All right, guys. Trig, identities, proofs, verifications, establishing identities, video 2. All right, so the focus of today's video will be still a lot more of the same stuff we did in the last video, but now we'll get a little bit more complex in terms of the algebra. So the factoring, the finding the LCD will just be a little bit more complex. This is the stuff now, and you've heard me say it a few times already. I'm going to say it 10,000 more times this year in this course. But in calculus, or calculus 2, or any other post-calculus course in college, it's not the new material that's so challenging. It's the algebra. So you've got to have that strong foundation in algebra. Otherwise, it just keeps coming back, and it just makes for stress and frustration. So we're going to focus on what I call the kind of the algebraic bag of tricks with a little bit more detail in this video. So our first example 9, just to let you know, there's not a new set of notes. We're just continuing with the set of notes you printed from our last video. All right, so if you have a fraction plus or minus a fraction, you have to get a common denominator. So the very first thing we're going to do is build two fractions with a common denominator. And there's kind of a shortcut for this, and we'll get to that a little later. But this was my original first fraction. I already have 1 minus sine as my denominator. I have cosine x as a factor in my other denominator. That's going to be my term I need to introduce. Minus, so my second original fraction, sine of x over cosine of x. And I'm going to multiply by, now the original fraction, the first fraction, has a denominator of 1 minus sine x, so that's the factor I need to introduce. So what's the reason here? All I've done is build an LCD, right? Created two fractions with the same denominator, and in this case the least common denominator. Okay, so you can call that algebra, whatever you want to call it. We found an LCD. Now I'm going to go ahead and simplify. So I have cosine of x times cosine of x, which is cosine squared of x, over my LCD, which is 1 minus sine of x times cosine of x, minus, and now I'm going to go ahead and distribute, so don't be upset with me, but I'm simplifying at this point. I have negative sine of x times 1, right, which is negative sine of x, and then I have negative sine of x times negative sine of x, which is plus sine squared of x, all over my common denominator. And I can move those terms around. I can make the terms look like this fraction. So I'm just going to put 1 minus sine of x first and cosine of x last. It doesn't matter. Now all I've done at this point is I've just simplified. I haven't done any trigonometry yet. All we've done is we've gone from two fractions being subtracted to a fraction plus a fraction, and now I'm going to build one fraction because I have a common denominator. And believe it or not, you will do a lot of this in calculus. So once again, I've just simplified. Nothing yet. Now here's where I'm going to do my famous hand wave, meaning I'm not giving a lot of explanation, but I kind of am. I know cosine squared of x plus sine squared of x. That's my OG Pythagorean ID. So I make a substitution. Cosine squared of x plus sine squared of x is 1 minus sine of x over 1 minus sine of x times cosine of x. I finally did a little bit of Trig, Pythagorean ID. That's my OG. All right, now off to the side, you don't have to write this, but I do want to make this clear. Off to the side, if I have A over A times B, all right, that simplifies to 1 over B. So you have an understood 1, right, as a factor there, so your A's divide out. That's exactly what we're about to do here, all right, just to make it more clear. I have a value divided by the same value times cosine of x. Here's what a lot of students will write. Don't do this, but a lot of students do. A lot of students will say that this is cosine of x. It's not. It's 1 over cosine of x. So understood to have a factor of 1 minus sine of x divided by 1 minus sine of x. I can only cancel out the 1 minus sine of x when I'm multiplying in the numerator by that value and multiplying something by that value in the denominator. So once again, all I've done is simplify. And then 1 over cosine of x is secant of x, end of proof, and that is my reciprocal, one of my reciprocal identities. So this one's a lot more complex than what we've done, but this is going to be something you do a lot in when you start finding derivatives in Calculus 1, which is a big deal. You'll be finding common denominators on a regular basis, even just so that you can simplify, right? So if I'm trying to find something relating to this as a function, it would be so much better to deal with just that. So it is nice to know that I can simplify this, and when I simplify this, it actually is just secant of x, much easier to deal with. All right, so that's our first example. Remember, the primary purpose of this problem was how do I go from adding or subtracting 2 fractions to just building 1 fraction with a common denominator, and in general, a lot of this stuff will divide out or reduce. All right, off to the next. Now, this problem, I've now at this point, off to the side, you don't see my work, but I've worked this problem 3 different ways. I want to show you guys how sometimes factoring will actually make a problem that looks complex initially will make it look a lot simpler. Here's what I mean by that. Okay, and once again, all of these problems can be proven to be simplified to a certain value multiple ways. Okay, but since this term has a sine squared of x, and this term also has a sine squared of x, I'm going to factor out sine squared of x first. It's going to look a little strange. Now when I factor out sine squared of x, I'm left with 1 over cotangent squared of x minus 1 over cosine squared of x. Okay? Looks strange, but all I've done is factored, or you could say that's the distributive property, because it is. Okay, either one of those are good justifications. All right, now I can make a substitution. I know that 1 over cotangent is tangent, so 1 over cotangent squared of x is just tangent squared of x. 1 over cosine squared of x is secant squared of x. Okay, now I used 2 different reciprocal identities, so those are reciprocal identities. Now, I'm going to have my, what I call in the classroom, if we were in the classroom, I have my little auxiliary board over here. So I'm about to do something that I have not done yet, but this is once again, these lessons, I know you're thinking, oh, we're just moving stuff around on paper. Guys, I cannot stress to you, this algebra that we're learning the next couple videos, the next couple weeks, is hugely important to being successful in any calculus or post-calculus course. So these are big deal concepts, not just something we're doing. Okay, there are some topics we learned that you'll never use again in another math course, but this is a big deal. Okay, so let me just write this off to the side. You know 5 minus 3, of course that's 2. You know 3 minus 5, of course that's negative 2. So anytime you swap the order of subtraction, you're finding opposites. Okay, and then you're like, duh, you know that. But to be more clear, I just want to make sure x minus y and y minus x are opposites. So here's what I'm about to do. I know one of my Pythagorean identities is secant squared of x minus tangent squared of x is 1. Well, that means that tangent squared of x minus secant squared of x is negative 1. Now, how do I know that tangent squared of x minus secant squared of x is negative 1? That's just one of my Pythagorean identities. Okay, and you can abbreviate that P-Y-T-H-I-D. Okay, so go back. Look at your list of 9, and one of those was secant squared of x minus tangent squared of x. So you just need to know that anytime you swap a subtraction problem, you flip a subtraction problem, you are in essence building the opposite. Okay? And then, of course, sine squared of x times negative 1 is just negative sine squared of x. How do I know that? Well, I simplified it. And I'll go back and forth, as you notice in my solutions. Sometimes I write simplify. Sometimes I write simplified. I'm doing that on purpose. I just want you guys to know that you're giving me a reason. When I say 2 times 3 is 6, I can say I used the substitution property. I could say I simplified. I could say I multiplied. I could say multiply. I'm just giving a reason. Okay, so the purpose is to write it as clearly as possible, making one substitution at a time, generally, and just giving a reason off to the side. And that reason has to correlate to the change that was made to the previous expression. All right. All right, so in example 11, you're actually given what the answer is supposed to be, cosecant of A times secant of A. But remember, the purpose is to justify. So this is a problem where right out of the gate, we want to rewrite every term in terms of sine and cosine. So tangent is sine over cosine. Cotangent is cosine over sine. What's my reason? Those are my quotient identities. Okay, now here's where I'm going to allow you to use what I call a shortcut, and I'm just going to write what the answer is. So I want you to watch this. I know I have cosine of A in my denominator. I need sine of A. So I'm going to multiply top and bottom here by sine of A. So that's going to be sine of A times sine of A, sine squared of A, plus cosine of A over sine of A. I need cosine of A. So I'm going to multiply top and bottom over here by cosine of A. So cosine of A times cosine of A. It looks almost like cross multiplication, which is how some middle school's teachers say it. I try not to say it that way. And then my common denominator needs to be cosine of A times sine of A. Now, if you're thinking, yeah, I know that, great. If you're like, what just happened? Let me squeeze in a little bit of kind of detail there. Okay, and I'll squeeze it in really lightly. So here's what it is. I know I have cosine of A. I need sine of A. So I'm going to multiply sine of A here over sine of A. So I need to introduce that. I know I have sine of A here, but I need cosine of A. So I'm going to multiply top and bottom by cosine of A. And it just so happens that every time I do this, what I just wrote in red, it always winds up being, if I'm simply introducing the numerator or the denominator from the left on the right, and the denominator from the right to the left, it winds up just being sine of A times sine of A, cosine of A times cosine of A, and then whatever this sign is drops down, and then your denominator will be the first denominator times the second denominator. Now, you absolutely do not have to use that shortcut, but it is a nice shortcut to use. Okay, and it's nice to be able to generate it to like fully understand where it came from. So all I did was what we did before. We established an LCD. We created a problem and we actually simplified. So if you just wrote LCD, that's fine, but we found the LCD and we simplified. Okay, once again, very little trigonometry. Most of what we're doing is the algebra. Okay, so now sine squared of A plus cosine squared of A is the OG Pythagorean ID. So that's the Pythagorean identity, and that's the OG. Then I'm going to actually split this. You can call it factoring if you like. Rewriting one fraction as a product of two. Okay, so I split the fraction. I really did factor. Once again, when you rewrite a number as a number times a number, you have factored the original expression. Okay, and the only reason I do that is to be pure. You can go straight from here to what I'm about to write. You know that 1 over cosine of A is secant of A, and you know that 1 over sine of A is cosecant of A, and that's what I was trying to show. Okay? Reciprocal identity. All right, end of proof. Little square in the corner if you want to. Okay, so that's it. So once again, the purpose of this problem was to show you how to find a least common denominator or any common denominator quickly. All right, off to the next. All right, so right out of the gate, I don't like cosecant. I'm going to rewrite it in terms of sine or cosine. In this case, cosecant of x is 1 over sine of x minus sine of x. That is one of my reciprocal IDs. All right, you'd think a math teacher would be more consistent. No, not necessarily. Okay, now I have a fraction minus a fraction. When I say a fraction, every number is a fraction, right? So I can rewrite this as a rational expression. Now, common denominator. I have 1 over sine of x minus, I can multiply top and bottom by sine of x here. You don't have to show this. You can simply just say that's sine squared of x over sine of x. When you rewrite sine of x as sine squared of x over sine of x, perfectly okay. Okay, so all you've done is create two fractions with a common denominator. Now I can actually subtract the two fractions. All I've done is simplify. Okay, now do a little Pythagorean identity. 1 minus sine squared of x is cosine squared of x. Okay, so that is the Pythagorean identity. Now, what in the world do I do with this? This is starting to look a little strange. I can split. Here's what I mean by that. I can rewrite this as cosine of x over sine of x times cosine of x. I can factor it. Split that fraction. Now, why did I do that? Because that's not very clean, but I do know what cosine of x over sine of x is. That's cotangent of x times cosine of x. And that's as simple as I can make this problem. And this is considered simpler than this. I don't want a square if I can avoid it. I don't want a fraction if I can avoid it. All I've done to get from this step to this step is use one of my quotient IDs. Simple as it gets. Okay? All right, off to the next. All right, let the algebra do the work for you. 1 plus a value times 1 minus a value is 1 times 1, 1, minus sine squared of b. What did I just do? All I did was the distributive property. Or FOIL. But it doesn't look like FOIL. So I'm going to, once again, dive into my auxiliary board here. I do want you guys to know that when you do x plus y times x minus y, you FOIL this out, x times x, x times negative y is negative xy, y times x is xy, and then y times negative y is negative y squared. The middle terms cancel out, and you're left with x squared minus y squared. I would be amiss, and I know you've seen this before. If you have, Mr. Young, I know you've seen this. This expression is called a difference of squares. Perfect square minus a perfect square. And when you factor x squared minus y squared, you get two binomials, which seems strange. You get x plus y times the conjugate x minus y. Okay, now we're going in the opposite direction. So we're taking a pair of conjugates, right? Y plus sine of b times y minus sine of b. And I know what x times x is. I know what 1 times 1 is. It's 1. I know what y times y is. It's y squared. I know what sine of b times sine of b is. It's sine squared of b. And then, of course, the pattern is you're subtracting, because a positive times a negative is a negative, so therefore you're subtracting. Okay? So anytime, I just want to make this clear, anytime you have a binomial times a binomial and there's what's called a conjugation, a number plus something, a number minus something, it will always give you a difference of squares. And so this actually is, you don't need the 2, but this is a perfect square minus a perfect square. Now, you could say difference of squares, you could give that as a reason, but all I've done, I didn't have to know that this was called a difference of squares to simplify it. So all I've done in this problem is I've multiplied it out, I've simplified it, I've used the distributive property, or I FOILed that. Any one of those, perfectly good explanation. Okay, so we have 1 minus sine squared of b, right? Just to kind of rewrite that because it was kind of muddled. Well, that's just cosine squared of b. How do I know that? Pythagorean ID. Done! End of proof. We have simplified. Okay, so you will see several. This was just an excuse for me to do one more of those. So 1 plus sine of b, 1 minus sine of b gives you a binomial. All right, guys, so start cranking out those problems, guys. Once again, for every one of these proofs, especially now that we're doing much more complex proofs, every one of the proofs I've just done, except for the very last one, really can be done multiple ways, all perfectly justified. Write every reason for every step of the way. Keep working, guys, and reach out if you have questions. All right, be safe.